All right. So this is something we are going to try to do today, and particularly on the shallow water equation again. So here our W is actually h, and h times x velocity and h times y velocity. That's our conserved quantities, the volume of water and the momentum of water. And our x directional flux is hux squared plus the pressure half of g times h squared, and h times ux uy. Our y-dimensional flux is similar, h of uy, h of ux uy, and h of uy squared plus half of g h squared. So this feed into our general finite volume, our general conservation law, dw dt plus x derivative of x flux plus y derivative of y flux is equal to 0. All right. So converted into finite volume scheme, we have time derivative of the area of triangle A, area of triangle I, times the Wi, which is a cell average. So this is equal to the integral over triangle I, right? W times dx. Okay, and then plus a summation of j within the neighbor of I, the flux. Okay, and here the flux I is equal to 0. Here the flux I is an approximation for an integral over an interface. And here we use a single point Gauss quadrature, which is equal to the flux evaluated at the interface center dot product with the normal, right? The normal times the size of the interface, or length of the interface, or the length of the edge. All right, any questions? All right, so for implementation, the way to work this out is actually most commonly follows a slightly different way as what's apparent in this formula. And this is because most of the computation cost is to figure out this Fi. And if you loop over all the, well, this is Fj, sorry. Right. So if you loop over I, which is loop over the areas, then each interface is shared between two different triangles. And the flux then is going to be computed twice for every interface. Right? Exactly the same numbers. Okay, except for a sign difference, right? Because the normal as seen from one triangle is exactly the opposite of the normal seen from the other triangle. But every other number is the same, just a sign difference. So the most common procedure is actually loop over the interfaces and compute the flux from one side of the interface to another side of the interface. And then we are going to add the same flux to one side of the interface and subtract exactly the same number from the other side. So it's going to be a loop through the interfaces. So let's try it over here. First of all, let's construct all the necessary ingredients for a finite volume scheme to work. And all the necessary ingredients are actually not a lot. So first of all, you need the area of each triangle. 2, you need the normal of every triangle multiplied, normal of every interface multiplied by the length of the edge, right? I mean, the normal is a unit vector, so multiplied by the length is just make it not a unit vector anymore. So we'll just call it a normal, a sized normal. So that's the second one. And the third one is you need to know which triangle has which interface. Or you need a mapping between the interfaces and the triangles. And for finite volume scheme, it's actually pretty easy to store that, because for every interface, you have exactly 2 volumes that shares it. So we store it in an array that has the length of the number of interfaces times 2. Right? The first dimension is the interface, and the second dimension is the cell on the left side or on the right side. And the value of this array stores which triangle, the index of the triangle. Okay, so this is can be done by first, for example, using the PD toolbox, and we can just draw some domains, and you can do it whichever way you want. Here, let's actually add another one like that. Okay, so we are going to discretize the domain using a mesh. Okay, and we can click on mesh and export the mesh. So the mesh is going to be exported in terms of points, edges, and triangles. So if you look over here, the edge, this actually contains a lot more information than you need, but it also doesn't have some of the information you need. So for example, points contains the points of the nodes, but nothing gives you, for example, the normal of the edges. Instead, the edge actually gives you, for example, the map between basically the index of these points, right, on the 2 sides of this edge. It also gives you the edge length, but like it's the edge normals we need is actually 90 degrees rotated from the edge vector, and it also gives you which domain it is in, but like we don't really need that for now. It also gives you the triangles, and the triangles is basically what are the 3 nodes that are on the nodes of the triangle. So this data structure is actually very suitable for finite element, but like it is not built for finite volume. So I wrote a code, a PD tool to FEM, just to compute the values necessary for finite volume. So for example, I have the I_tri, which is which triangle is on the left and right side of every edge interface, and the normal vector of every interface, and also the area of every triangle. So these are the 3 numbers we'll need. So we'll call this, and basically it populates the workspace with some additional variables we're going to use in our finite volume code.